2, 1, go. Well, happy to see you. Thank you for submitting homeworks. Yeah, I'll walk in and pick it up. And thank you for staying in the class. I wouldn't say today's meeting is completely useless. Thank you. It will be very closely related to the next homework. And we need to stay in this particle in the box a little longer, but we need to think out of box. So in the little example that, oh Nate, how are you? So in the little example that we covered, so you solved time independent Schrödinger equation, and then for one specific boundary initial condition, you solve time dependent Schrödinger equation. But in this example, we looked in the system, in the example where there are very few electronic states, like first and second, and the rest of states didn't contribute to our analysis of the model. And this can be the case if in real life, in true physical chemistry, if you deal with atoms and very small molecules, where a couple of orbitals, which are eigenstates of the Schrödinger equation, play an important role in the chemistry and properties. But as you can imagine, realistic molecules and materials have lots of ions, lots of electrons, and number of eigenstates is quite high. So we do have a big challenge even without going into the any other potential. So we can stay within particle in the box, but target describing some realistic models, and we do need one more theoretical tool, one more. It's not something advanced and challenging. We cannot call it a method, but we need a way how to approach the situations when we have many electronic states. And the challenge is that if there are like a handful, we can draw them or speak them and give them names. But if there are like thousands of states, it's not a human nature. I know, how are you? So if there are thousands of states, it's not practical to name all of them, and it will be boring for human nature. And if you want to set up a program for a computer to count states and analyze them, we still need to get an idea what we are looking for. So the new material today will be very brief. It can be squeezed in 3 minutes. So I'm trying to expand, make very short story long. Why? Because this new concept that we will cover today will help you to do your next homework, and because it will be a fundamental for next couple of meetings. And third, because it is would be really interesting and important to those who decide at one day to look at computational chemistry. So there is the concept designed to analyze multiple electronic states is widely used there, and if any one of you in the future career decides to touch this area of knowledge, it will be like a background and fundamental. Okay. Let me share screen. So please teach me what do you see here on the screen. How do you call this object? Huh? Okay, a sail. Which types of sails do you know? I was when preparing for today's meeting, I looked that there is like main sail, front sail. There are multiple names, and if one looks into parts, I recognize that I never used this words in regular life. But if you look through the list of many, for example, students in the freshman class, you recognize that some of these names are coming as a family names. You may have seen that the language of sailing left, even we are not using this rigs. It's only luxury yachts by now, but it left the trace in the civilization in the family names because it was popular. So what's the shape of this mainsail? Okay, so in some sense, our meeting will be dealing with two objects. One is a triangle shape of sails, and another is strawman. So if it will be not a lecture but a piece in the theater, here are our actors. And we will go through mathematical equations, but you'll see connection to these objects, and maybe it will create a little spark to memorization and remember things that we go over today. So I looked online to several examples, and this specific ship looks very similar to what we need to get mathematically. So we are going to get the shape that is almost triangle, but it is based on the right angle, same as the standing pole, and then it goes only to one side and goes not in a straight line, but with a little curvature. So this object will be used to analyze systems. It is a result of analysis of systems where number of states is very large, and when they are really dense, really close to each other. And in today's class, we will get only the first of the sails. But in your homework, you will get several. And it will be one of the questions to analyze why there are more than one sails on this yacht. And who is here? How would you call this object? Yeah, strawman. So I was trying to express associations and way how we get to this equation by visual language of hands. But last year, students of last year told me, do not spend your efforts. You are trying to explain what is strawman. So it will be a good help to go over today's material. Okay, so density of states, discrete and continuous definitions. And thank you for submitting homeworks. I really enjoyed reading and watching them. You did very meticulous and dedicated analysis, and I especially liked the verbal analysis that I saw. So here's the next one, which is due next Monday. So it will be very similar to this one. Run the code and generate figures and analyze them, same as in wet chemistry lab works. As a minimal task, you will need just to manipulate these three numbers, rerun, and then see what happens and analyze. And there is a promise that by manipulating these three numbers, which are equal to 20, and changing them in the range maybe from 20 to 300, one of the images will get to this three-sail yacht. So this is quite easy, and I sort of need to apologize. We need to do another homework, and it will be due not in a Monday from now, but earlier on Wednesday. And this one will be in some way harder than the one based on the MATLAB. I really would prefer to have it later, but to match the class material, we need to a little concentrate and speed up and try to do it. And there will be no MATLAB, but it will be like credited as an independent homework. And I will keep explaining what it is. It will be kind of terminal homework on the particle in the box, and you see that it will deal with predicting the expectation value of position where the electron is in the particle on the box. And as we go through this week, we'll go over this matrix elements of the position operator, which you are acquainted with through our previous practices. And most of you already did math of this task by doing extra credit 2 homeworks ago. So remember when you had sine x times sine 2x times x dx. So basically it is this piece. So in about 10 days. Okay, so we do browse in the 3-dimensional space of ideas, models, and external perturbations. And by now we have only free space and 1-dimensional box. Relatively soon. As soon as we will be done with that homework, we'll go to more systems. And we are getting through few additional concepts for the purpose that the simpler the object we are looking at, the simpler is the math to get new concepts. And later on, we may use them again and simplify our life, not in a sense that this course will become simple. It's not out of my control, but we can find some shortcuts by selecting one or another tool from the toolbox. So the concept that we are getting over today is so-called density of states, and you already, I hope, made a screenshot in your heads of the Sale and Stroman. Right? So I will be very happy if we, it's not if, when we arrive to the equation that looks like 1 over square root of energy, and when we will be able to overlay this function with sail on a yacht. So it's, in some sense, it is my goal. And I invite you to invest your attention in finding connection between this image and the concept of particle in the box. A little earlier, those are 2 equations. I should have copied these ugly caricatures here, but those are 2 equations that we are supposed to memorize or at least recognize. So the eigenfunction and eigenenergy, which is proportional to number of the states squared, right? So in some sense, we are almost done. The rest are mathematical details. Well, I'll try to entertain you, but it will be quite quick. So for any chemical system, there is one can apply either pen and paper calculations or computational calculations and find wave functions and eigenenergies. And let me ask those of you who did practice UVVs or any spectroscopy, like NMR, anyone practice spectroscopy? Okay, good. And 2 hands means practiced really intense. Okay, so how would you define what is the spectroscopy and what is its goal if you have a family member, a sibling who is in the kindergarten, and by some reason he or she asks what is spectroscopy and who needs it. Interview from Wyatt last time.
You have an unknown something, and it's a machine that gives you numbers so you can try to figure out what that unknown is.
Excellent. I like it very much. Let's check. Sibyl, do you want to add something to what Wyatt told?
Basically, usually, for example, if we're talking about UVs, it emits light into the unknown object, into our sample, and that unknown object absorbs certain type of lights in the different wave functions or whatever. And then we get in the screen, we see absorbance versus wave function. And basically each unknown sample has a corresponding wave absorbance at a certain wave function. And by that, we can compare and determine which unknown sample or molecule it's in our solution.
Excellent. Yeah, thank you. I really like your view, and I'm trying to match them together. So Adam, what do you want to add to this discussion?
I think they said it pretty well. I was just going to say it helps us identify what an unknown is or what something might contain.
Okay. Yep. Laura, would you like to add something?
So spectroscopy is finding the composition of a substance based on how it can absorb certain wavelengths of light.
Okay, yeah, thank you. So I'm very happy to hear your interviews, and it matches very much to what I would say myself. And your stories are better than mine, but I would summarize it that by response of the object to like external perturbation, one can identify such signatures, which are like wavelengths of absorption, which allow to identify the object. So it can be considered even as reverse engineering. By looking on the signatures, one can reconstruct which object gave these signatures, because we accumulated database of several substances, and by their signatures we can reconstruct what it was, right? So it deals very closely to eigenstates of Schrödinger equation. So basically those transition wavelengths are the offsets, differences between energies of the eigenstates, right? And now an analysis of these energies of eigenstates with some connections through instruments helps to identify what was the original system that generates the states, right? And if there are few electrons, if there are discrete states, like in atomic spectroscopy, then it will be just set of lines. But if you have big molecules or pieces of solids, nanostructures, what do you think would happen to these lines? Or if you have molecule with vibrational sublevels, are they really straight thin lines, or they have some width? Some widths, right? So they, instead of lines, it will be some shapes and profiles. So this transition from discrete to continuous distribution is what we need to start addressing today. So if there are more than few states, the eigenstates of a model, of a molecule, can be analyzed not as one by one, but as a whole thing by describing the distributions, continuous distributions that will tell us at which energies there are more energies and at which energies there are less. Make sense? Okay. And in some sense, I can tell again that we are done. There will be a few more things, but they will be mathematical. So we will provide a little bit of mathematical muscles and very little derivation behind this words. Let's focus on the screen. So, who is that? Yes. So we'll teach Strawman the eigenstates of particle in the box. So let's set up the lab work for Strawman the following way. The Strawman walks from 0 to infinity, from left to the right. The axis is energy of eigenstate divided by energy of the ground state, which dimensionless will be just n squared. And we give an assignment to Strawman to walk forward and look backward. Is it doable? Yeah, nothing challenging. And the Strawman needs to take lab notebook and record how many eigenstates he saw behind his back at a certain time. Make sense? And if we got a lazy Strawman, we can allow him not to write it by text, but just make a graph. How the number of states behind his back depends on the amount of steps he made. And when he starts from 0, there is nothing behind him. When he passes the number 1, there is 1 step behind him. Then we go n squared, next number is 4, not changing. Then when he passes the figure 4, it increases by 1. When he goes further, when he passes 9, it increases by 1 again. When reaches 16, increases by 1 again, reaches 25. And then it's like a stairs with unequal size. So how can we call this number, the observations that Strawman made? What did he record? Just it's not a tricky question. Let's try to launch our creative imagination and give name for this observable. Right. It's kind of made up because it is already written. So number of states. So he counts number of states behind his back. Okay. How would this so we need to analyze this number of, we do see that this number of states deals with features of this system, of the particle in the box. And we can put our attention in 2 limits. One limit when this E naught is very big and these steps are far from each other, and another limit when E naught is small and they're close to each other. So what can we do if E naught is big? So we can ask our Strawman to make another record each time the step in number of states occur. So each time he walks and sees that something happens, he can just put a little stick, right? Or if the straw man is in a rush and doesn't have skill to draw the exact stick, he can just put the hand, straw hand, like up and down, and it will be a set of peaks, each of which will appear at the energy of the eigenstate. Make sense? So when states are close to each other, these lines may overlap. When they're far from each other, the space between states will be 0. So this all goes quite close to our human intuition. And these sticks can be mathematically expressed as delta functions. So we have peak when energy is equal to energy of eigenstate. And we add together several peaks to have this distribution. So, but what should we do if they come really close to each other? We can also make another definition, which would work if they become denser. We can count number of states per interval. So if per certain interval there are, like in this interval there is nothing, 0. In this interval there are 2. So it's more, the states are dense to each other, which means in this interval they are denser. There is a higher density of states. Make sense? Okay, thank you. So and when you will likely take the PCAM2, they will, the next course will use density of states as number of states per volume or per energy range. But this definition is more appropriate for states which are predominantly dense. If they are sparse, this definition is much better and it is more universal. But still, let's look onto the situation when states are dense. So nothing new. There should be, and I know that it is, and probably you suspect and already know it, the simple words that I was trying to deliver should have a way to be expressed in mathematical language. So when we are telling that at a time when there is a step, we make a peak, can be related to derivative, right? When the height changes instantaneously, it will be infinite jump. Or opposite, if the area under the peak is 1, we can integrate this function. When we integrate area with a running upper limit, there is 0, 0, 0, 1, and then nothing, it 1, 1, 1, 1, 1 step, it becomes 2, right? So there should be, and there is a mathematical way to convert upper figure and lower figure from to and from without a straw man. And if number of states is n and the upper line is derivative, then it would match our definition for high density. How many states are located per energy interval, which would be number of states divided by energy interval, or we can call it as derivative of n over e. Yes? Okay. So here are mathematical tools that I think Joshua was introducing on the last presentation. And do I need to go over them, or you have seen them in the past, and it's objects you deal with every day? Yes, no, not sure. Okay, so not everyone is 100% sure. So there are two standardized mathematical objects made specifically for the problem we are trying to address. And in this abstract concepts, in these symbols, there is no challenge at all. It's only mathematical language to integrate our common sense analysis with procedure of differentiation and integration. So when there is a peak, we define it as Dirac delta, right? And it is infinity at a point when argument agrees with this point placed here, x minus x naught, and the area under this infinitely tall curve is assumed to be 1, and the width is assumed to be as close to 0 as possible. So one can tell that it is infinity in the center and 0 before and after. If one integrates this function with a running upper limit, yeah, sure, with a running upper limit, it will become 1 if we pass this point x naught, and it will be 0 if we before it, right? So step function. And the common symbol for this function is Greek theta, which if you feel uncomfortable drawing this calligraphy, you can just make 0 and cross it. And it was used by a person with last name Heaviside and used mostly for engineering problems. But one can tell Heaviside step function or Heaviside theta function. And integral of delta will be theta, and opposite. If one makes derivative of the theta function, then one will get the delta function. One shouldn't try to do it. It's just definitions. There are two functions connected by calculus procedures, integration, differentiation, which would correspond to step with discontinuity of 1 and infinitely tall peak. Enough? Good. Okay. So we are going to connect these things. And by the way, if you already know that our particle in the box gives energy which escalates as n squared, basically this one will be density of states for discrete case, right? If we integrate it, we should get number of states. And if we really want to illustrate this mathematical concepts in MATLAB with finite differences, it will be quite discomfortable because our step size is always bigger than 0, and we do not know at which point it should instantaneously jump. There is a trick when that the Gaussian function with appropriate normalization and in the limit of the width parameter going to 0 is a very good approximation for delta function. So whenever you do see the symbol of delta function, one can safely replace it by Gaussian and just assign very small width parameter. So all mathematical definitions are expected to work. So if you take derivative of Gaussian, it will be like step, but it will be not abrupt and sharp. It will be like a little, like if we make a step out of ice or sugar and then try to lick it or pour water on it, it will be a little shallower than original. Now, let's set up a little experiment in our heads. Suppose we do have peaks corresponding to each of eigenstate, right? We add them together and get set of peaks, which would correspond to this, like all peaks together. Now, what would happen if we abandon approximation of zero width and try to increase width? I'm tired to speak. I'll go to interview mode. Nate, I'm going to ask you and Joe second, because you didn't give interview in the previous. So what would happen to this distribution if we keep increasing the width?
They'll start to overlap with each other. Like it looks like that bottom graph is kind of the.
So they will start overlap, and what would happen to our overall height?
Oh, it would lower. Yeah.
It would, where would it lower, and where would it
In
get any
the
higher at any
yeah, it would lower at the where the peaks are, and then it would get higher everywhere else basically. Because
Okay.
right.
Okay, yeah, thank you. And let me formulate the question. If we are not looking for absolute heights, but we are comparing maximal available to minimal available heights. Like originally on this first figure, we see as a standalone, right? And the heights maximal in here, maximum in there is approximately the same. If we go into a limit of very heavy overlap, would the absolute height here and there the same or change?
I don't think it would change, right? Or
If you go to a really heavy width parameter, if you do it not like 0.1 or 1, if you make width equal 10, so it will be bigger than offset.
oh yeah, then I think the closer you are to the more dense that the states are, the lower they'll be, and then the less dense is they'll be higher.
Okay, yeah, thank you, Joe. Nate, agree? Everyone agrees? Okay, yeah, thank you. So if you go into the limit of very heavy, if the width is bigger than offsets, then it will be higher where the states are denser and lower where they're sparser. Okay, so it is the effect that I want to catch by a little mathematical derivation, which will be the actual lecture. Everything else is just preparation. So we need to mathematically catch this effect that density of states is higher where states are denser, and it is lower when they are sparser. So what is shown here? I should be able to tell it myself, but please try to identify and tell what is shown in the upper panel. What are the axes? Let's go in a second circle.
Just as energy is a function of the number of states.
Okay, excellent. I do not need any more help. It really works. So energy as number of function of states. Yeah, thank you, Adam. What do you think about and what's a functional shape? So it's in normalization initial energy, and then it goes as quadratic, right? And here we automatically go from discrete to continuous limit, right? We, instead of putting points and nothing between them, we assume that they're so close that it is a continuous function. And this is a main approximation. And this is a main background for all next derivation, even I didn't wrote it and we just informally tell it. So continuous function that grows quadratically. Now, this is function of energy as number of states. Can we, based on this expression, express number of states as function of energy? So what would it be? I see that Wyatt wants to answer. So how do we invert function if you swap argument and function?
The square root of energy over E naught.
Yes. So if the direct function is square, inverse will be square root. Yep. Thank you. If the function is more complicated and I do not know the functional form, how would I invert a function? Like exponential that goes up and logarithm that is inverted. If we make a section of our plane with 45 degrees, they will be like a mirror image. Right? And if we look on this square root, it will, we just flip the image in respect to this 45-degree thing, right? So we can graphically just draw function and then flip the image to swap the independent variable and the function. Okay. I even do not know how to write it, but we did a tremendous amount of intellectual effort for this work. So we do have analytical pen and paper expression for number of states as function of energy, right? Square root of energy, which looks like it gets smaller and smaller, right? Well, it increases with decreasing slope. Increasing with decreasing slope. So, and we need to get a density of states. What is the definition of density of states? Thank you, Sibel. You are disclosing the answer and removing intrigue from the recordings, but well, formal definition, unspecific for this problem. Just tell how did you get it?
Right.
Just repeat once again if someone is watching.
If you take the derivative,
Yes.
and then
Yes.
you'll be left with yeah, then you'll be 1 over E naught times the square root of energy.
Mm-hmm.
Yeah.
Yeah, thank you so much. So did everyone agrees and hears? So density of states is a derivative of number of states over energy. So we look how many states are per energy interval. So we are taking, taking this much minus this much divided by this delta E. Delta N divided by the delta E. So when the slope is big, basically it's slope of this curve. When the slope is big, density of states will be higher, which means they are denser. When the slope is smaller, the slope will be small, which means they're sparser. Better? So we just practice definition of the density of states, which is a derivative of number of states. And as Sibel already taught us, it will be if you take a derivative of the square root. So when we take a derivative of a polynomial function, what happens to the power? Huh? And what else? Is it increases or decreases? Decreases by 1, right? So you will get energy to the power -1/2. Yes, my clone a year ago agrees with you. So energy to power e to the -1/2. And how do we plot it? How do we draw it? So if we please show me in the air the function 1 over x. How does 1 over x depends on x? Can you just draw it in the air? Adam, good. Nate? You're showing negative values. And if x is bigger than 0, can you draw it once again in the air?
I was drawing from my point of view, I guess.
But it starts from higher and goes to lower, right?
Yeah.
So if x is 0 plus small number, it will be infinity. 1 divided by 0. So it starts with top and drop. Yes, better. Everyone agrees? Okay. Now, what would happen to the function if it's not? So 1 over x, which will mean x to the power -1, right? If the power is a little more shallower, it will be the same feature, but not as sharp, right? So 1 over x. And if we have shallower power, like x -1/2 or something, it should go not as aggressive, right? Okay. So we took derivative, we find this thing. And now I need to speak again. This morning I did send to everyone a link to Wikipedia, which you do not need to read. It's only if you have nothing else to do, which I doubt. But there are ways to measure density of states on experiment, not only compute and predict, not only convert it later to the spectra, but there is a direct way to measure density of states, which one way is electrochemistry, when you do this redox stuff, right? So it's peaks as function of voltage offset, but voltage is like energy per electron. And one way it shows peaks of the unoccupied, another for occupied. Another option is so-called scanning tunneling microscopy, when one puts a tip in vacuum above the sample and makes current to leak from between substrate with 1 voltage and tip needle with another voltage. And if the offset of this voltage matches the energy of certain orbital, it will give a peak in the signal, in the current. So I'm just showing it here, STM experiment. If we do it not for model, abstract model of 1 electron in 1 infinite box, but if we make apply it to realistic systems when there are other dimensions, they just play less significant role, you will see that in addition to 1 peak, there are a few more. And we should discuss it on the lab and next meeting. And if we take the shape of this 1 over square root of energy, an unhealthy imagination can find connections to a seal, right? So I believe we did arrive to the goal. I think this ship that I found in the internet is Spirit of Bermuda. So thank you for your patience. Meeting is done. Everyone is welcome to disconnect and depart. I'll stay here a few seconds to check if there are more questions.